Welcome to today's paper reading. Today's paper is titled, xLSTM, Extended Long Short-Term Memory. This paper was published on the AR14 preprint by Maximilian Beck and colleagues from the LS Unit, Lit AI Lab, Institute for Machine Learning, JKU Linz, Austria. The abstract introduces the forward pass of the MLSTM for a single head, simplifying the head dimension. It discusses the construction of the forget gate activation matrix F and the input gate pre-activation matrix I. The abstract also mentions the application of the element-wise exponential input gate activation function and the need for numerical stabilization to avoid overflow. Additionally, it covers the parallel computation of hidden state pre-activations using queries, keys, and values, and the application of the output gate in parallel for each time step. Figure 1 provides an overview of the extended LSTM, xLSTM, family, detailing the evolution from the original LSTM memory cell to the new xLSTM and MLSTM variants. The original LSTM is depicted with its constant error carousel and gating mechanisms. The new xLSTM introduces exponential gating and a novel memory mixing technique, enhancing the LSTM's ability to revise storage decisions. The MLSTM, on the other hand, is fully parallelizable and features a matrix memory cell state with a new covariance update rule, addressing the limited storage capacities of traditional LSTMs. These advancements are integrated into residual blocks to form xLSTM blocks, which are then stacked to create an xLSTM architecture, showcasing the progression and improvements within the LSTM family. Figure 2 illustrates the limitations of LSTM in two specific tasks: the nearest neighbor search problem and rare token prediction on Wikitext 103. On the left, the nearest neighbor search problem is depicted in terms of mean squared error, MSE. Given a reference vector, a sequence is scanned sequentially for the most similar vector, aiming to return its attached value at the sequence end. LSTM struggles to revise a stored value when a more similar vector is found. Our new xLSTM overcomes this limitation by employing exponential gating, which allows for more effective revision of stored values. On the right, the rare token prediction task shows the perplexity, PPL, of token prediction on Wikitext 103, categorized by token frequency. LSTM performs poorly on predicting rare tokens due to its limited storage capacities. In contrast, our new xLSTM addresses this issue by utilizing a matrix memory, which enhances its ability to handle and predict rare tokens more effectively. Figure 3 illustrates the two main types of xLSTM blocks: the residual xLSTM block with post-up projection and the residual MLSTM block with pre-up projection. On the left, the xLSTM block processes the input through an xLSTM layer, which may include an optional convolution, followed by a gated multilayer perceptron, MLP. This structure is similar to that of transformers. On the right, the MLSTM block is embedded within two MLPs, featuring a convolution, a learnable skip connection, and an output gate that operates component-wise. These detailed configurations are further explained in Figures 9 and 10 in the appendix. Figure 4 illustrates the performance of xLSTM's exponential gating with memory mixing on various formal language tasks. The results are presented as scaled accuracy, where 0 indicates random performance, and 1 signifies perfect accuracy. The tasks are categorized according to the Chomsky hierarchy, reflecting their complexity. Notably, some tasks require state tracking, a capability that xLSTM demonstrates effectively compared to other models like transformers and state space models, which are shown to be less powerful in this context. Figure 5 illustrates the memory capacities of various models and the multi-query associative recall task, with a context length of 2048. Each panel corresponds to a different number of key-value pairs. The x-axis represents the model size, while the y-axis indicates the validation accuracy. This setup allows for a comprehensive evaluation of the model's ability to recall key-value pairs under increasing complexity. Table 1 presents a comparison of various models on the task of next token prediction after training on 15 billion tokens from Slim Pajama. The table highlights the best validation perplexities within different model classes, including transformers, LSTMs, SSMs, RNNs, and linear transformers. Notably, xLSTMs with new memory, xLSTM 1 o'clock, and xLSTM 7:1, achieve the best performance, outperforming other methods. These top-performing methods are subsequently utilized in Section 4.3 for Large Language Model (LLM) training. Table 2 presents the results of ablation studies focusing on the new components of xLSTM. The top section of the table shows that the strong performance improvement of xLSTM over vanilla LSTM is attributed to both the exponential gating and the matrix memory. The bottom section of the table investigates different gating techniques, concluding that having each gate learnable and influenced by the input has an incremental positive effect. The study considers an xLSTM 1 o'clock with a sigmoid forget gate and an exponential input gate, with various bias initializations. The validation perplexity, PPL, is reported, and the dependencies of the gates on the input lead to better performance. Figure 7 presents a comparison of 1.3B sized models from xLSTM, RWKV4, Llama, and Mamba in language modeling, focusing on next token prediction after training on 300B tokens from Slim Pajama. The models were trained with a context length of 2048 and tested up to 16,384. The left side shows token perplexities at various context lengths, highlighting that xLSTM models maintain low perplexities for extended contexts, unlike other methods. The right side evaluates prediction quality in terms of validation perplexity, PPL, when extrapolating to long contexts, where xLSTM achieves the best PPL values. Table 3 presents a comparison of xLSTM, RWKV4, Llama, and Mamba models in terms of validation set perplexity and performance on downstream tasks. The models were trained on 300B tokens from Slim Pajama, with sizes ranging from 125M to 1.3B parameters. The table highlights that xLSTM 1 o'clock and xLSTM 7:1 models achieve the lowest perplexity on the validation set. Across various downstream tasks, xLSTM generally outperforms the other models, with Mamba occasionally excelling on the ARC task. The table provides detailed metrics for each model's performance, with the best performing models for each size indicated in bold and the second best underlined. Table 4 presents the performance comparison of xLSTM, RWKV4, Llama, and Mamba on the Paloma language modeling tasks. The models were evaluated based on the perplexity of next token prediction after training on 300B tokens from Slim Pajama. The model sizes range from 125M to 1.3B, with the second column indicating the actual number of parameters. The 571 text domains are categorized into language modeling and fine-grained domain benchmarks. The last column displays the average perplexity across all tasks. The best model for each model size is highlighted in bold, with the second best underlined. Notably, xLSTM demonstrates superior performance, particularly xLSTM 1 o'clock, which achieves a lower perplexity in 99.5% of the text domains compared to Mamba, and in 85.1% of the domains compared to Llama. Additionally, xLSTM 1 o'clock outperforms xLSTM 7:1 on these language tasks, further emphasizing its effectiveness. Figure 8 illustrates the scaling laws for next token prediction perplexity among xLSTM, RWKV4, Llama, and Mamba models. These models were trained on 300 billion tokens from the Slim Pajama dataset, with sizes ranging from 125 million to 1.3 billion parameters. The figure highlights the best performing models for each class, as detailed in Table 1. The scaling behavior shows that xLSTM outperforms other models, particularly indicating its favorable performance for larger models compared to transformers and state space models. Figure 9 illustrates the structure of an xLSTM block with post-up projection. The input is first optionally processed through a causal convolution with a window size of 4, which includes a swish activation for the input and forget gates. The input is then fed into a block diagonal linear layer with 4 diagonal blocks or heads. These heads correspond to the recurrent gate preactivations from the last hidden state, effectively forming an xLSTM with 4 heads. The resulting hidden state is passed through a group norm layer, which performs headwise layer norm for each of the 4 heads. Finally, the output is up and down projected using a gated MLP, which employs a GLU activation function and a projection factor of 4/3 to match the parameters. Figure 10 illustrates the architecture of an LSTM block within a pre-layer norm residual structure. The input is initially up-projected with a projection factor of 2, serving 2 purposes, one for an externalized output gate and the other for the LSTM cells. The LSTM cell input undergoes a dimension-wise causal convolution with a kernel size of 4, followed by a learnable skip connection. Inputs Q and K are derived through block diagonal projection matrices of block size 4, while values V bypass the convolution step. Post-sequence mixing, outputs are normalized using group norm, specifically a headwise layer norm for each of the 4 heads. The learnable skip input is then combined, and the result is gated component-wise with the external output gate before being down-projected. Figure 11 presents supplementary results on the scaled accuracy of various models in solving formal language tasks. These tasks are categorized according to the Chomsky hierarchy. Notably, none of the models achieved a minimum scaled accuracy of 0.3, indicating challenges in task extrapolation to larger context lengths. Among the evaluated models, xLSTM demonstrated the best performance. The authors introduce MQAR, a new evaluation method designed to capture associative recall (AR) performance differences in language models. This method is particularly useful for analyzing the memory capacity of large language models (LLM), with transformer models like Llama serving as the benchmark due to their exponential memory encoding dimensions. The experimental setup involves 2 key variables, context length (CL) and number of key value pairs (KV), both of which influence the difficulty of the recall task. Additionally, a fixed vocabulary size of 8,192 is used across all experiments. The experiments employ 2 blocks or layers for all models, with varying learning rates and batch sizes dependent on context length. Training includes cosine annealing with a warm-up period and uses Atom W optimizer with a weight decay of 0.1. In Experiment 1, xLSTM 1:1 and xLSTM 1 o'clock demonstrated the ability to solve tasks across all model dimensions, outperforming other models like Hyena and RWKV4. The exponential gating mechanism in xLSTM variants notably improved the model's autoregressive capabilities. Experiment 2 revealed that while scaling context length had minimal impact, xLSTM 1:1 and xLSTM 1 o'clock showed no performance decay, unlike RWKV models which consistently lost performance with increased context lengths. Experiment 3 extrapolation results indicated that xLSTM 1:1 and xLSTM 1 o'clock maintained their performance, with RWKV models experiencing slight degradation. Overall, xLSTM 1:1 emerged as the best performing non-transformer model, suggesting enhanced memory capacity, especially in long contexts. Figure 12 illustrates the setup of the multi-query associative recall (MQAR) task. In this task, color pairs represent key-value pairs, with keys having a darker shade. The first part of the sequence defines the key-value pairs for each sample. Following this, keys appear randomly according to a power law distribution. Gray tokens in the input sequence represent 0 tokens. The target sequence contains the value after the respective key appearance, with the rest of the tokens ignored for accuracy and loss calculation. The model's task is to predict the value tokens given the respective key. Figure 13 presents the results of MQAR Experiment 1, which evaluates various models on increasing task difficulty by simultaneously increasing context length and number of key-value pairs. The columns represent different task settings, while the rows group related models for better clarity. The x-axis indicates the model size, and the y-axis shows the validation accuracy. This setup allows for a detailed comparison of how different models perform under varying conditions of context length and key-value pairs. Table 5 provides the model hyperparameters used in each of the long-range arena tasks. It specifies the embedding dimensions, batch sizes, and training steps for tasks such as retrieval, ListOps, Pathfinder, Gimage, and RGBimage. The table ensures that the best learning rate and the better of two learning rate schedulers were used for each model. Figure 14 presents the results of MQAR Experiment 2, focusing on the impact of scaling context length on model performance. Notably, xLSTM 1:1 and xLSTM 1:00 maintain stable performance without clear decay, while both RWKV variants exhibit slight, consistent performance loss with increasing context lengths. The varying number of key-value pairs significantly impacts all models, with RWKV5 outperforming RWKV6 in certain settings. Overall, xLSTM 1:1 emerges as the best-performing non-transformer model, suggesting enhanced memory capacity, especially in long contexts. Table 6 presents the test accuracy results from the long-range ARENA benchmark. The table highlights the best-performing model in bold, the second best underlined, and models that failed to outperform random baselines within X. xLSTM is identified as the top performer among xLSTM 1:00 and xLSTM 0:1, based on validation dataset accuracy. The table also includes the performance of Llama, Mamba, and RWKV4 models, providing a comprehensive view of their accuracy in various tasks. Figure 15 presents the extrapolation results from MQAR Experiment 3. The models, including xLSTM 1:1, xLSTM 1:00, and Mamba, were trained on a context length of 2048. The evaluation was conducted at different context lengths, showing that xLSTM 1:1 maintains its superior performance from Experiment 2. RWKV models, particularly RWKV5, shows slight degradation with increasing context length. The x-axis represents the model size, and the y-axis represents the validation accuracy. Table 7 presents the peak learning rates and model dimensions crucial for understanding scaling laws and model performance. It highlights the optimal learning rates for models like RWKV4, Llama, Mamba, and xLSTM across different parameter sizes. The table also details the model dimensions, providing insights into how these factors influence the training dynamics and final model capabilities. This data is essential for researchers and practitioners aiming to optimize their models for specific tasks and datasets. Table 8 presents the performance of different matrix memory configurations. The study reveals that the matrix memory within the pre-up projection block yields the best results, leading to the xLSTM 1:00. Notably, the inclusion of a dimension-wise causal convolution in this block is identified as a significant factor for optimal performance. In this section, the authors describe the experimental setup for training their models. They follow a general training procedure and train models of two sizes, 1.3 billion parameters and 2.7 billion parameters. The context length used during training is 2048, and the batch size is set to 256. The peak learning rates for these models are taken from Table 7. Additionally, the authors provide a link to a GitHub repository, although no further details are given about its contents. The authors employ a consistent training procedure for xLSTM large language models, using a context length of 2048 tokens. The models are trained with varying batch sizes and training steps, specifically 256 for 600K steps for smaller models and 512 for 300K steps for larger models. For downstream evaluation, the authors utilize the LM evaluation harness to assess performance on tasks such as Lambda, Heliswag, and Pika, reporting accuracy and accuracy normalized by sequence length. The evaluation is conducted in full float 32, full float 16, and float 16 mixed precision with weights in float 32. The Paloma dataset, comprising 16 of its 18 data sources, is used for additional evaluation, with all models assessed in float 16 mixed precision. Perplexity values are reported for each data source, providing a comprehensive view of model performance across different domains. Table 9 presents the perplexity values for various models across different domains including Twitter AE, Manosphere, 4chan, and GB. The models evaluated are RWKV4, Llama, Mamba, xLSTM, 1:00, and xLSTM 7:1. The text documents are split into sequences of length 2048 tokens, corresponding to the pre-training context length of all models. For documents longer than 2048 tokens, non-overlapping input sequences are created, with the last sequence filled up to 2048 tokens, but perplexity is computed only on the remaining tokens. The perplexity values for the Paloma language model are calculated using the exponential of the negative log likelihoods, which are then weighted by the number of tokens per domain. This method is defined in Magnussen et al. 2023, equation 1. The detailed results show perplexity values for each of the 571 subdomains of Paloma, as reported in Table 10. It's important to note that the aggregated perplexity values in Table 4 are not simple macro averages of those in Table 10. The dataset exhibits significant variability in perplexity, with notable differences observed across different models such as Llama, Mamba, and RWKV4. This variability highlights the impact of domain-specific tokens on the model's performance. In this conclusion, we compare the performance of different models across various datasets. Specifically, we look at how Mamba, Llama, and RWKV4 xLSTM 7:1, xLSTM 1 o'clock models perform on datasets like Dolma_100_subreddits_val, Falconry FindWeb_val, and Gab_val. The key metrics we focus on are accuracy scores, which show how well each model predicts outcomes, and the consistency of these scores across different models. We also observe the variability in performance across different datasets, highlighting areas where certain models excel or fall short. This analysis provides a comprehensive view of the strengths and weaknesses of each model in different contexts. Thank you for watching.